Righty. Thank you all for being here. So as the speaker said, I am David Budnitsky. I studied computer engineering at Tux, and I'm currently working as a bit of a back-end, mostly back-end, somewhat front-end, very bad front-end dev at APSA. So without further ado, today I'm going to be taking you guys on a quick little trip down encryption lane. If I can share my screen. Okay, so to kick us off, I'll be explaining a couple models and ideas that we need to use, or that you guys just need to at least be familiar with. And after that, we'll look at a couple different ciphers that all employ different techniques. So first, we'll look at substitution ciphers. Specifically, we'll look at the Caesar cipher. Next up, we'll look at stream ciphers, specifically RC4, also known as Riva cipher 4. And lastly, we'll look at some block ciphers, and we'll specifically look at the data encryption standard, or DES. Alrighty, now to kick us off with the models, obviously encryption is used to hide data or to protect our data. So over here, we've essentially just got a typical communication system. So on your left, you'll have a sender who wants to send some secret message to the guy on my right, or yeah, on your right, who's the receiver. So in order to do that, that message has to be transmitted. But you don't want anyone to know what you're sending. So in order to do that, you're going to encrypt your message. So you'll take the plain text and you'll pump that through some form of encryption algorithm to get your cipher text. After that, you'll transmit that. Then that'll be received on the receiver side. After that, whatever you've received will still be the cipher text, which then needs to be decrypted to obtain your plain text. And plain text because you kind of want it to look the same as what you originally set. Okay, so now that we've got that down, let's have a look at confusion and diffusion. So confusion essentially aims to make the question of what is this in the ciphertext, like just as difficult to answer as possible. So in a bit more of a technical context, that means that one bit in the ciphertext essentially needs to depend on many bits from your key, which I'll touch on later. And after that, diffusion kind of wants you to struggle to answer the question, where is that in the ciphertext? So especially in the case at the bottom here, we can't really see much. But here, very little diffusion or confusion is added because this picture of a banana is still very clear here. The banana is just purple instead of yellow, and the background is just maroon instead of pink. And then over here, we've got something, we don't know what, in the middle on some background, but we can still see that it's somewhat similar. So essentially in here, we'll have quite a bit of confusion because we don't exactly know what this is, but there's not too much diffusion because we can still see there's something in the middle on some form of background. All right, so now that we have all of that down, let's have a look at our first cipher. And for that, we'll talk about the substitution cipher, specifically the Caesar cipher. So in general, substitution ciphers simply just swap or shift some information in your plain text based on your key to get your cipher text, okay? And your key is normally just a number that tells you how big that swap or shift has to be. And in order to show this to you, I'm going to show you how the Caesar cipher works. So before I get there, we've got a picture of Julius Caesar asking for 5 beers, which I think is quite funny. Alrighty, so let's have a look at how the Caesar cipher works. Does anyone want to select a picture for me? Anything specific? Jenna? It's the cat. Okay, cool. Alrighty, so over here we've got a cat with glasses. And how the Caesar cipher works is, or at least with images, I need to select a key between 0 and 255. So Batandwa, do you want to give me a key or just a number between 0 and 255? You're on 64. Cool. Alrighty. So now if I hit my encrypt button, that's what it looks like. So see that's just a cat with glasses on a background. It's just different colors. So this doesn't really encrypt our image much. And because of that, we can say that the Caesar cipher doesn't really add much confusion or diffusion to our picture because we can still see it's a cat and we can still see the cat in the middle of the photo. Alrighty, so now that we've had a look at that, let's have a look at the next cipher, which is RC4. So in general, stream ciphers make use of a stream of values that you can do something with that value and your cipher text to get, and your plain text, sorry, to get your cipher text. So yeah, in the case of RC4, we use some form of stream generation to get a stream of pseudo-random numbers. Those have to be pseudo-random because by definition, anything that's encrypted needs to be decrypted. So that means that your encryption algorithm needs to be deterministic. So those pseudo-random numbers need to be able to be, you have to essentially be able to get them over and over again in the same order in order to encrypt and decrypt. So now that we've spoken a little bit about that, let's have a look at RC4. So I'll change cipher to RC4. Just how RC4 works, I do need a bit more of a complicated key. And that's what we get from RC4. So quite a lot of confusion and diffusion, in my opinion. I mean, if you can tell me that there's a cat in here, I'm going to tell you to go to a doctor because something's wrong. And if you can see a cat, I also want to know where. That's just what I want to add. So yeah, that's how the RC4 algorithm works. And now that we're here, I'll actually get the block cipher, DES, going. And just for simplicity and to kind of have it like a fair comparison, I'll use the same key and I'll get the encryption going. And for now, we can have a look at DES, or block ciphers, and then we'll have a look at what DES does to our data. So in general, block ciphers, as the name would suggest, processes your data in blocks, okay? And those blocks are normally of fixed length, and the cipher itself also uses a fixed length key. So while the demo is still running, I'll just explain how the algorithm over here works. So on your right-hand side of the picture, we've got this very, very complicated key generation or key expansion algorithm rather. And on the left, we essentially see that we have a 64-bit plain text, and that's the block length in this case. And because we have a 64-bit plain text, the DES specification says that we need 16 rounds of encryption with an initial permutation. And before any rounds are performed, after your 16 rounds, you have a 32-bit swap where you'll essentially take your 64-bit plain, your 64 bits, you'll take 32 bits on the left, 32 bits on the right, and as your 32-bit swap says, just swap. Very complicated. And after that, you've got your inverse initial permutation, which is just another way of shuffling things around that should hopefully add to some form of diffusion. And after that, you'll have your 64-bit ciphertext just for that block. Alrighty, so now that we've had a general idea as to how DES works, let's just have a look at what the ciphertext is. So once again, if you tell me that there's a cat in this picture, I'm going to probably send you to a doctor. However, one thing that you can see is that there's like a bunch of pixels over here and over here that look like they might have some information. And essentially how DES works is in its diffusion, it literally spreads the information. So you can think of it as if you have like a puddle of oil on a table and you just go with like a very, very bad cloth and just spread it across your table. That's almost what DES does with data that it's encrypting. So essentially with DES, we can say that there's quite a lot of confusion because I can't see that this is a cat, but there's also a lot of diffusion because I can't see where the cat is, but I can kind of see that some data from the glasses is, or most likely from the glasses, is sitting around here and here. So now that we've looked at general encryption and the three different encryption schemes,